previously in lecture. Why don't you try this one here? So follow the steps, balance this one in basic conditions, and see what you come up with. Then we'll go through it to make. All right, here we go. The first thing we want to do is not skip this problem and do it. So we're going to split it off into the half reactions. So once again, we just want to put together things of the same elements. So I see an I minus there. I see an I over here, which is an I2. I also have an Mn in this side, and I got a little MnO2 over there. So again, really just want to split it off into the half reactions to start it out. We also, it's really a good idea to identify what's being oxidized, what's being reduced, and we could use our oxidation states to do that. Also, again, as you saw earlier, it will kind of help you make sure that you're putting things in the right spot as you kind of are going through. The last thing you want to do is get to the end and go, wow, I really messed that up there and not really working right. So if we look at the oxidation states of our I minus, that is -1. We have a -2 for the oxygen there. There's 8 of them, and it equals -1, which means the Mn in this case is a +7 that's happening. Question on that? No? Okay. I2 is how it naturally comes, which means it is a 0 oxidation state. The oxygen over here is a -2. There are 2 of them. It's the -4. It is a neutral guy, which means in this case, the Mn is going to be +4 in this case. Any questions on how I got my oxidation states or numbers there? So again, if you're not sure, you could roll to your number line to help you out. Hopefully that's helpful. We could look at the I, and the I starts at -1, which is here. And on the right-hand side, it ends at 0, which means it is moving in this direction, the more positive direction, which means it's actually going through oxidation. By the way, as I mentioned before, if you can identify one, you know by default the other guy is doing the opposite thing, which is the reduction. You could also do the number line for the other guy as well, and we would look at the Mn in this case. The Mn is +7, which is like here. And on the right-hand side, it is +4, it looks like, right? Which means it is moving in that direction, which is becoming more negative and is going through reduction. First off, any questions on that? That would mean my oxidizing agent is which one? Which one's my oxidizing agent? That would be my oxidizing agent. As that is being reduced, that is my reducing agent because that is being oxidized. So remember that the agents are opposite of sort of their name, basically. Yeah. Question on that there. All right, so now that we kind of know what everybody is going on here, the next thing that you want to do after you split it off, let's get that out of the way. The next thing you want to do after you split it off is you want to balance all the elements except for oxygen and hydrogen. So in this case, we do need to do that with the first one. We just need to put a 2 in front of the I to give us 2 I's on each side. Again, the ultimate goal here when you balance these is for them to be balanced like a normal equation, that you got the same number of elements on each side. And again, that the overall charge on each side is the same. In terms of the bottom one, we do not need to put a coefficient because we basically have one Mn on the left and one on the right. So again, we don't need to do that there. Once we've done that, we're now going to move to oxygen. Since there is no oxygen in the top one, we will move to the second one that has oxygen. In this case, we actually have 4 oxygens on the left and we have 2 on the right, which means to balance out the oxygens, we would need to add 2 waters to the right-hand side. That's going to give us our 4 oxygens that we need total. But again, because we added 2 waters, we do have to add the H pluses to the opposite side. Otherwise, we're going to be short. So we will have 4 H pluses here to the left-hand side. Any questions on that there? My question is, where did it go? There it is. All right. Now that we've taken care of the oxygens and the hydrogens, which we really didn't have too much going on here, the next thing we want to do is actually balance the charge on each side. And this is where we're going to add our electrons. So again, the electrons are negatively charged. So we do have to add it to whichever side that needs the negative to get us to an equal number of charge on each side. And again, this does not have to be 0. So on the left-hand side here, we basically have a -2 overall from the I minus. Over here, we have 0, which means that the right-hand side in this case actually needs 2 electrons. And that will give us a -2 on the right to match the -2 charge we have on the left. Any questions on that? Based on my identification of this being the oxidation half reaction, did I just add the electrons to the correct side? I did. They should always be on the product side, right? If it's oxidation, and that's where I put them. So this is where you could check yourself to make sure that you're doing it correctly, or at least in that sense. When we look on the second equation, this guy's going to provide a +4. This overall thing here will provide a -1. Once again, I'm just going to go with the overall charge. Why go individual? Because that's basically what the overall charge equals. That gives me a +3 overall. Right-hand side, that looks like a 0, and that looks like a 0, which gives me an overall of 0 on the right-hand side. That means that to get us to an equal number of charge on each side, because we're adding negative electrons, we're going to need to lay up 3 electrons on the left-hand side here. That will give us a -3, which gives us a 0 on the left to match the 0 charge there on the right. Any questions on that so far? Yeah. I2 is one of those diatomic elements, so that's how it naturally comes. So it's just like H2, N2, O2, any of the halogens, right? It comes as 2s, and that's just naturally how they come. So even though there's 2 of them together, technically they're uncombined with any other element. So they're in their natural state, and they'll have an oxidation state of 0. O2 as well would be, O2 by itself would be 0. The MnO2 is not the elemental form of oxygen because it's attached to the Mn. So it will have the -2 oxidation state in that case. It would not be the -1 because it's really not peroxide, if that's your kind of other question. Yeah. Oh, I'm sorry. The overall charge of that thing is a neutral species, is not an ion. So that's manganese 4 oxide. So there's no overall charge. So the overall charge is 0 on it. Yeah. Other questions? Okay. So now that we've added our electrons, we're almost in the home stretch here. We want to add them back together. But once again here, we cannot add these back together until we have the same number of electrons in each half reaction, which in this case, we do not. We have in the first half reaction 2 electrons. In the second one, we have 3. So in this case, we actually need to multiply both of them by a number. The common number, obviously, between 2 and 3 is 6. So the goal here is to get to 6 electrons in each half reaction. That's going to require us to take the first half reaction and multiply by 3. And the second half reaction, we need to multiply by 2. So I'm just going to rewrite that underneath after I multiply it through. So multiplying the top reaction there, that's going to give me 6 of the I minus goes to 3 of the I2 plus 6 electrons. Multiplying the 2 on the bottom reaction gives me 6 electrons plus 8 of the H pluses plus 2 of the MnO4 minus, 2 of the MnO2, and 4 of the water. So all I did is basically just distribute those numbers across everybody in each half reaction. Now I actually do have the same number of electrons in opposite half reactions. Also, like we talked about earlier, you should always have the electrons on opposite sides. So if you're ever adding electrons and they end up on the same side, you definitely did something incorrect. So they always got to cancel out completely. That will cancel out the 6 electrons as they're on opposite sides of the arrow in the different equations. And I think that is all that's going to cancel out here. So if we take everything down, everybody on the left-hand side will stay there. So 8 H pluses plus 2 of the MnO4 minus plus 6 of the iodine. Everybody on the right-hand side will stay there as well. 3 of the I2 plus 2 of the MnO2 and 4 waters in this case. Yeah. Now, if I were to have wanted the answer in acidic conditions, that would be it. Yeah, that would be my balance equation in acidic conditions. I have 8 hydrogens on the left, 8 on the right. I have 2 of the Mn on the left, 2 on the right, 6 of the iodines on the left, 6 on the right, 8 oxygens on the left, 4 and 4 is 8 on the right. Overall charge on the left-hand side is a +8, a -2, and a -6, which is 0. Overall charge on the right-hand side is 0. Everything balances out. So if you were to do this one in acidic conditions, you would put a box on it and you would be done at this point. First off, any questions up to this point? Now, since we are doing this in basic conditions, this is the way I would recommend doing it, which is do it in acidic conditions. Now we're going to turn this into basic conditions. And I know this is acidic conditions at this point because I see H plus in my equation. So that tells me this is balanced in acidic conditions. So to turn it to basic conditions, this is the part where we add OH minus to both sides, and it's going to be equal to the number of H pluses I have. So in this case, I have 8 H pluses, which means I'm going to add 8 OH minuses to the left and 8 of the OH minuses to the right. Once again, on the side where you have OH minus and H plus, these guys are going to come together to make 8 waters in this case. And usually what happens in this basic condition is you'll have some waters to cancel. So on the right-hand side, we have 4 waters. On the left-hand side, we have 8 waters. So if I subtract the 4 from each side, that's going to leave me a net of 4 waters that's left over. I will still have my 2 MnO4 minus and my 6 iodines on the left. And nothing else is going to change really on the right here. So my 3 I2s, my 2 of the MnO2, and my 8 OH minuses. And now if I did this correctly, I should still be balanced. And this would be 8 hydrogens on the left, 8 on the right. I have 4 oxygens in the first guy and 8 in the second, which is 12. I have 8 oxygens on the last one and 4 in the middle, which is 12. 2 MNs on both sides, 6 I's on both sides. Overall charge on the left is a -2, -6, and 0, which is a -8. Over here, it is a -8, as everything else here is zeros, basically. So again, it is balanced both ways, both in terms of elements on each side and overall charges. Any questions on that one there? Yes, no? Good. All right, one more for good measure. Yes, just to make sure. You'll thank me later. I'm not sure what part you'll thank me at, but maybe you'll say a few other things that I don't want to hear before you thank me, but maybe you'll thank me at some point. All right, let's just roll to this, not that one. Let's roll to, let's do this one right here in acidic conditions. Let's balance this guy in acidic conditions. Should be a cakewalk now. Cake does sound good. All right, so this one we're going to do acidic. We're going to do the same approach. We're just going to pair up everybody that is similar. So I see a chromium in this guy. I also see a chromium over here. And I see a carbon. I was going to say copper. I don't know. Carbon here and a carbon here. All right. So again, we're going to figure out what's going on in terms of oxidation reduction. So it can be helpful a little bit down the road. We did this guy earlier. So once again, this guy ended up at a -2, which is a -14, equaling a -2 overall. And there's 2 of these guys, which means each one's going to be +6. That gives us a +12. That gives us a -2 overall. Over here, this is our friend oxalate. That's a -2. That's a -8. Needs to equal -2. Once again, here we need a +6 to get us there. And there's 2 of them, which means each of these guys is going to be a +3, right? That gives us a +6. Going to the right-hand side, that's chromium-3, which is the easiest of all of them. It is a +3. And that is a oxygen. That's a -2. That's a -4. This is neutral, which means it needs to add up to 0. And that means that the carbon here will be +4 in this case. Any questions on assigning those oxidation numbers? All right, so to figure out what's going on here, we'll do our little number line. So if we look at the chromium on the left, starting at +6. And on the right-hand side, it's ending at +3, which means it is moving in the negative direction, which means this guy is being reduced in this case. And by default, that means this guy is going to be oxidized, and we could do the same thing with the carbon here. That's a +3 to start with. And on the right-hand side, it's a +4, which means it's moving in a positive direction. And it is being oxidized, right? So it is this guy being oxidized. That also means that the chromium, our dichromate here, is our oxidizing agent. And the oxalate is our reducing agent. Any questions on any of those identification purposes here? All right. So now that we've split it off, again, you do not want to forget the first step after that, which is you do want to balance all of the elements other than oxygen and hydrogen. And in this case, we do need a 2 right about there for our chromiums. And we also need a 2 there for our carbon as well, right? So we got to take the 2's in both of those spots. Any questions on that? Next is going to be oxygen action here. We got 7 right about there, which means the right-hand side is going to need 7 waters. And because I added 7 waters to the right, I put 14 hydrogens over there, which means we're going to add 14 hydrogens over here to the left-hand side. Do I need to add water to the bottom one? I actually do not. I got 4 there, and by putting that 2, I have 4 there, which means that took care of that for us pretty nicely. So you actually do not need to add water to the bottom. That does sometimes happen, so you want to make sure you take that coefficient into account. Any questions on that there? All right, at this point, we're going to add electrons, and we're going to look at overall charge on each side. And let's see here. That's a plus 14. This is a -2, which means I got like a plus 12 working on the left-hand side. Over here is going to be a plus 6. And this is going to be a 0 in this case, right? So in this case, we need to get them to the same number, and I'm adding negative electrons, which means I do need to actually add it to the left-hand side here. And I need 6 electrons to do that. That will give me a -6 here, which gives me a grand total of plus 6 on the left to match our plus 6 on the right. I also know I added it to the correct side because this is our reduction half reaction, which means my electron should always be on the reactant side. So again, that is a way you could check yourself to make sure that you hopefully did it correctly. Any questions on any of that there? Looking at the bottom one, we got overall charge -2. Overall charge here 0. That means bottom right here, we need a couple of electrons to give us a -2 on both sides in this case, yeah? Any questions up to that point? All right, last thing we need to do is we're ready to add this together, but we have different numbers of electrons in each half reaction. Top one is 6 electrons. Bottom one is 2 electrons. That means we do need to multiply the bottom guy by 3. I'm just going to recopy both of the equations on the bottom here. So that's going to give us 6 electrons for the top one that we didn't do anything to, plus our H pluses, our dichromate, our 2 of the Cr3+, and our 7 waters. We're going to multiply this 3 to everybody on the bottom. 3 of these. Gives us 6 of these and 6 electrons. That means at this point, we're ready to add together. Electrons, like we should always see, completely cancels out. Everybody on the left is going to stay on the left. So that's going to give us 14 H pluses plus our Cr2O72 minus plus our 3 of our oxalate. Going to give us on the right-hand side, everybody will stay there on the right-hand side. So I'm just copying everybody that's on the right-hand side as I add them together. And if I did this correctly, we should be balanced in acidic conditions. I know it's acidic because, again, I see the H plus here. So just to make sure, I got 14 H's there. I got 14 right about there. I got 2 CRs. I got 6 carbons. I have 7 oxygens there, plus 12 more is a lot. 19 maybe. I have 12 oxygens there, and 7 more makes 19. Overall charge, plus 14, minus 2, minus 6. Plus, what we got there? 6, I think. I got that right? I hope. On the right-hand side, we got plus 6, 0, and 0. So that is a winner right about there, yeah. If I wanted basic, all I would have to do at this point is 14 OH minuses to both sides, combine the water and reduce down the water, and then I would have it into basic conditions at that point. Making more sense? Yes, as we do more? Yeah. Okay. Just got to make sure you recopy things correctly as you do it. Question on how to balance.